I do not. No audio. Yep. We're good? Awesome. And thanks to Adrian as well for recording all these. This is awesome. Who's ready to break some stuff? Anybody? How many breakers are in the room? Do we have people that break professionally? All right, cool. I don't think there could be a better time for a conference that has a crypto focus than right now. It's been in the front page of the newspapers probably for the last 2 or 3 weeks. It's got its fair share of time slots, late night news. With all the crypto stuff that's going on, it's an incredibly important thing for us as a community to focus on. And it's moved out of the realm of technologists and it's moved into a social realm. Now that we have these things as the center of a lot of debate, people that aren't just nerds are starting to think about crypto. And so one of the things I think that we can do is get tunnel vision. And so today I'm going to look at certain ways that we can bypass encryption and break it. So we'll have some chance to break some things. But first I wanted to define what a cryptosystem is. I kind of sort of more or less made that up, so I'll put an example to it. When you talk crypto, there are a bunch of characters that most cryptologists know, and the two most common ones are Alice and Bob. And so when you have Alice that wants to send a message to Bob, you've got to find a way to share that securely. So the first step is to come up with a key. There's a lot of different ways that you can do it. You can use a secure key exchange algorithm. You can meet up with each other and exchange the keys. That doesn't really matter, but the point is each person has to have a key. Symmetric, asymmetric, whatever, but there has to be some way that you can communicate some shared secret. Alice then takes the key and uses it to encrypt a document. That document then is safe, and she can send it to Bob. Bob then can take his key and decrypt the document. So Crypto 101, right? And when we look at attackers, I think that we most typically think about the character Eve. Eve is definitely a character that we need to be concerned about. She is by far the most prevalent on the network. She could be anybody between you and the point that you're connecting to. So you saw the last talk about all the crypto. If your Tor exit node isn't encrypted, right, that you can read that traffic. Eve is anybody that's listening to that communication. If you're on unencrypted wireless, anybody could be Eve. So it's a very prevalent attacker. The potential for Eves is very, very great. That said, I think we tend to tunnel vision on Eve and forget a couple of the other attackers. So one of the things that I think is interesting to point out is that at both ends of this crypto system, you have Alice and Bob both with a key and both with plain text. And there are ways that we can try to get to that without actually going at the crypto itself. So there's another character that's referenced quite a lot less, but Mallory is a character that can see traffic, but also has the ability to manipulate traffic. And this is most often used in things like oracles. So you'll have a user that manipulates encryption to see if it comes back with some type of error, and then you can send it over and over, and hopefully you get it to leak some type of data. That's the most common use case, but I'm going to show some other ways that you can actually use this character to attack the endpoint. The other character wasn't even defined. I made it up. I'm going to call him Red for Red Team. And it makes sense that he's not defined because it's really outside of the protocol, but I think that we need to start thinking about this character when we're designing crypto. He is somebody that has access to the system and is able to look over Alice or Bob's shoulder. And he can have differing levels of access. It could be full system compromise, it could be user level, but some level of access to that system. And so I'm going to show attacks from those 2 points of views as we go. I'm going to run through these fairly quickly. I recorded a lot of technical demos ahead of time. They're going to move fast. If you have any questions, I will try to address them. Just raise your hand, yell out, and I'll see if I can take care of it. So there's a couple of ways that we can attack the endpoint directly. The most obvious or straightforward is probably just looking at the running process itself. And I think one of the ways that you can do that fairly easily is by looking at memory. So I want to demonstrate how bad some applications can deal with memory. And it's because they weren't necessarily built to deal with memory securely. Their goal was more speed and functionality over secure data storage and memory. So first thing we're going to do is browse to an HTTPS website. Next, we're going to log into an application. We're going to go ahead and close the tab, wait for a few seconds, and then we're going to do a process memory dump and see what we can find. So I decided to pick Firefox and Linux for this demo. So hopefully you can see that. The resolution's a little bit different than prior. So we'll browse to the capturethecon website for this conference, and it's over HTTPS. As you can see, we're going to go ahead and log in and type the username and password. Before we do that, we're going to go ahead and inspect the element and get what the username or the parameter is that we'll be posting to. That'll just help it to search through memory a little bit quicker for the demo's sake, but it could be really anything. So we'll log in. We're going to say not remember the password because of security, right? And then we're going to close out of the tab. We'll find the process ID for Firefox, and then we're going to use a tool called gcore on Linux to run the process dump. In this case, I'm running it as root. You could do it as the same level of the user that is running Firefox if you had those level of privileges. Next, we're going to encode the parameter that we're looking for so that we can see what it would be like as a URL encoded value. And then we're going to go ahead and grep through the dump using strings and grep to find that code. And you can see that in memory, even after we closed the tab and waited for a little while, there is the credential. So this is a way to show that your browser is a great place for looking. If you're doing a pen test and you get onto a box, do a core dump on the processor. Pull the memory and see what passwords are still there, because you're going to find a whole lot of stuff. Anything that's been posted, you can usually pull out of memory for some amount of time at least, so that you can see the session password. So that's an easy example. I wanted to show something a little bit more technical, something a little bit more fun. So we're going to do some process injection. This is actually a vulnerability that I was able to do responsible disclosure on about 3 months ago, but I haven't really released any of the details yet. So you guys will get to be some of the first to have the live demo. Oh, actually, no, sorry, wrong demo. I'm going to demo VeraCrypt, which is also kind of fun, but it's not their fault. So don't go saying VeraCrypt's terrible because of this. The one day will be later. So in this case, we're going to do some injection. We're going to inject a process into VeraCrypt. If you have access to the system, you can view whatever the application is doing. So we're going to use API Monitor to see what VeraCrypt is doing when it starts up. And then we're going to use Immunity Debugger to take a closer look at the code as it runs. For those of you who aren't familiar with VeraCrypt, it's the replacement for TrueCrypt. It's the one that got picked up and is now being maintained as supposedly the secure alternative. So first, and I apologize that this is a little bit smaller than I expected, but we're going to go ahead and start VeraCrypt in Process Monitor. You can see that it starts up. We're going to go ahead and stop the process, and then we're going to add some filters. Before we do that, we're going to look at what we're trying to attack. So if you pull up the password prompt, you can see that it uses the typical looking Windows that pops up, and it's got the password prompt. So we're going to go ahead and use the Windows Application UI filter, and we're going to do Windows and Messaging, and we're going to look at the Windows tab. If you expand that and look through some of the calls that it makes, and these are calls that you can hook to the Windows API. So as the program communicates with Windows on the back end, you can view what is going on and what is being sent to those calls. So we're just going to hook all of the Windows related functions in user 32, and we're going to reattach to VeraCrypt. So now we're going to pop up the VeraCrypt again. We're going to go ahead and say we want to mount something securely, and then we see some traffic. We're going to type in our credential here, and it's going to start trying to decrypt the drive. And you can see some more traffic kind of over there to the right. As we look at a little bit closer at the calls that it's making, you can see that there is a get window request. And if you look at the parameter that's being sent to that, it is the password that was sent via that form. So the Windows is using the tool is using the Windows API to communicate back and forth and to pull the value out of that password form. So that gives us a place that we can potentially hook with process injection. So next we're going to start up Immunity Debugger. Immunity Debugger allows us to look at the assembly language and the stack, the heap, the memory as the process is actually running, so we can see what it's doing in real time. So we're going to load VeraCrypt again, and we saw that our function was that get window w function. So we're going to look at the executable modules, and we're going to pick the exe itself, and we're going to view all of the imports. So this is showing all the different DLLs that it's imported, the methods that they can call. From there, we're going to find the function that we want to set a breakpoint on, which is that get window. So if you look through, there's a ton of things that you could potentially breakpoint on and see what's going on. But there's the one that we're going after. So I'm going to go ahead and right click, and then I'm going to say set breakpoint for every reference. I don't know where it is in the code, but I don't want to spend forever looking, and it's a lot easier usually just to set a breakpoint on everything and then run the application, wait till it breaks. So we'll go ahead and hit play and let it start up the application. Veracrypt is now going to start with the immunity debugger attached. When we go ahead and click the button once, it breaks. So we're going to go ahead and let it continue and then run it again. You can see that there's another breakpoint at a call to get Windows text W. So the code is calling that API function. We're going to go ahead and say step over, and we're going to take a look at the stack. And so this is where things are essentially being stored in part of the memory, right? And you can see that the credential is now pushed onto the stack after that call is made. And if you look down the list, you can see that the next thing that's called is this wide character to multi-byte. And further down, you can see that there's some password checking that it does before it tries to decrypt the container. So this wide character seems like it'd be a better one to attach to. It's probably called less. So we're going to set a password hook on that one. And so the next step then is going to be set up a process to actually do some injection. So we're going to create a new function that will look like that wide character to multi-byte function that will save output to file and then call the original multi-byte. Then we're going to use a tool called minhook, which is essentially a cheap version of Windows detours. It allows us to hook a process. It's out on GitHub. You can download it. It's really easy to use. And then we're going to create reflective DLL using another tool. If you search for GitHub and reflective DLL, I think the guy's name is Stephen Fewer. It's also out on GitHub. It's an awesome project. But joining those two together, we can inject code into any running process, and we can hook functions together. So those two together are actually a pretty powerful combination. So we're going to inject a DLL into Veracrypt. Just to look at the code very quickly. If anybody done C programming, show of hands, a couple people. Okay, cool. So when you do programming in C, you'll usually have a main function. A DLL is in the same way essentially, except that you're going to have a case statement that says why is a DLL being used, and one of the calls is when this DLL is attached. So when the application loads a DLL, it's going to call this get process attached, and it's going to run the code. So what we're going to do is we're going to start this min hook. We're going to create a hook, and then we're going to go ahead and run it. Once it's attached, this is a really crappy way to do it, but it's short and makes it easy for the demo. We're going to open up a log file just called verilog.txt. We're going to write the value of the parameter that's being passed to that wide character to multi-byte to the file. We're going to close the file, and then we're going to send everything back to the original wide character to multi-byte function so that it doesn't know that anything happened behind the scenes tricky. Right? So this is what it looks like when it actually runs. You can see, again, we're here at the create volume. We're going to go ahead and say, just to show this is a current and patch version, right? This isn't old, it's new as of a couple weeks ago. So we're going to find the process ID again. We're going to inject our code, so inject that DLL into the process ID of Veracrypt. And we're going to go and mount the drive, type in the credential, say OK, wait for a second. You can see that everything works fine as I expected. The drive was mounted successfully. But when we pull up Notepad and look at the Veracrypt log, there's some output, and at the very end of it, you can see thank you Windows, because their API made it easy. So again, you need to have access to the user's account. You have to have the ability to inject code into that process. But as a pen tester, once you get on a system, this is a great way to actually capture creds for something as sensitive as a full disk encrypted container. So questions on that before I move on to the next one? No? Cool. So you can attack the process. You can also backdoor the tools. So this is an old trick. It's been around for pretty much as long as computers have, but you can create a wrapper script. So we're going to create a folder that's accessible to a victim user. We're going to add a pseudo wrapper script to the folder. We're going to update bashrc of the victim so that the path will include the new folder that we created. And then we'll wait for the user to run sudo. And then we'll look at the log files for creds. So similar to before, but we're using a bash wrapper instead of DLL injection. So here we're making our folder and user share, so it's accessible. It doesn't have to be root user, again, as long as it's a user that can create a file that the user can see and can modify the victim's bashrc. I just Google searched for sudo bash wrapper or bash backdoor. This was the first thing that came up. So I actually didn't write this. I stole it, but it works great. So Google's your friend when you're looking at this type of stuff. But the script basically just will take all the input to sudo. It'll emulate the password prompt and then save everything to the file, and then it'll pass it back on to sudo. So we're going to make it executable. We're going to add the backdoor folder here to the user's path. And then we're going to go ahead and change it into the user just to show what it'll look like. So we're now acting as you can see we do sudo to root user. So he did sudo as the victim user. You can see that it cats out the password from the victim user. So there's a credential. Everything works fine. Sudo looks like it should work. But now you've got a credential with a bash script, and you didn't even have to change the original binary. So it's kind of a fun little trick if you need to get creds off of sudo. Here's another one. This is an older demo that I've done, but I thought it was relevant. So for those of you that use Debian or Ubuntu or any of those, you can use apt-get source, which is kind of a cool little trick. If you want to look at the source code of anything that's available, instead of doing apt-get install, just do apt-get source, and it will download the source to the local folder. So we're going to apt-get SSH's source code. We're going to look for ''S's password, because whenever you log into something, it says user's password, username ''S's password. So we'll look for that. We'll patch SSH, and then we're going to see if we can review logs for credentials. Here's the code. So we did the search, and we can see down at the bottom that there is a S and printf. So it's essentially printing the string of the user's name and the host that they're connecting to. And then the next thing is a read passphrase function. So that seems like a good place to mess with. So we're going to do the same thing. We're going to open up a log file. After that password read, we're just going to write that value plus the user's name to the file. So we'll recompile SSH, and now this is what it will look like when the user runs it. So here you can see SSH works as fine, as normal. It asks for the key. Users accepts it. They type in the credential. Typed in the wrong password, so it asks for another one. Type in the password again, and they've authenticated successfully. If we exit out and then look at the temp file that we created, you can see that it contains the user's password. So again, we can backdoor SSH with just a few lines of code. Excuse me. So any questions on any of those attacks? So those are fun, but you actually have to have access to the system, right? You have to have some level of access, whether it be user or in some cases administrative. But there's a couple other fun things that we can do to attack the endpoint directly. So this is the one day that I was talking about where it's been disclosed responsibly. They've patched it, and actually these guys were really, really good at fixing it. They took care of it within about a week of me disclosing it. But we're going to use procmon to watch what DLLs do on KeyPassX when it opens on startup. So KeyPassX is a key store that works for multiple systems. We're going to create some test DLLs. We're going to use the test DLLs, and we're going to see if we can keylog the process. So, and we'll end with an interpreter shell. So to define this, we're going to use procmon on Windows. We're going to undo everything except for the files so that we don't have a whole lot of output. We'll go ahead and start up KeyPass, run a couple of things, and then close out. We'll stop the capture, and then we're going to set some filters. First, we're going to scroll down and then exclude everything so that we're only looking at KeyPassX. And we'll set two filters. The first I'm going to use is an exclude, and we'll exclude everything that's not a DLL. So in process monitor, the path is an OR statement instead of an AND. So you can do a double negative with exclude to make it so that you can do an exclude and an add. So exclude everything that's not a DLL, and then we'll add everything that is in the current user's directory. For DLL injection, the way that Windows loads DLLs is it goes through a certain chain. And it will look through a series of places, but if it can't find what it's looking for, it will actually look in the current directory that the application is being run in some cases. And so if we filter down to everything that's in the users folder, you'll notice that I'll wait for it to, we're going to look for anything that's not found. So any DLL that the application can't find, it looks for a DLL, tries to load it, but it can't find it. In this case, you can see that we ran it from the desktop, and it's trying to load this WinTab32 DLL from the desktop, which shows me that we might be able to take some control over the system that way. So our goal is to create another DLL here and see if we can trick KeyPass into loading that DLL when it starts up. So this is very similar to before. The simple DLL is just going to open up owned by DLL hijacking just to make sure that everything's working. A more complicated one is a super basic keylogger. It's going to actually attach a keylogger onto Windows so that once it attaches, we can see anything that that user does, even if it's not in KeePass. And I will not bother with the code for now. So here's what it looks like. You can see it opens normally, no issues. But if we copy over a DLL, this is our test DLL, to the desktop, and then we open up the application, you can see that it pops up a prompt, which shows that I have code execution now in that process. So let's get a little bit more creative. In this case, we can pretend that there's a shared network drive. For the sake of time and simplicity, I just created a shared file drive. But you can imagine in a corporate environment where everybody shares files, or you have a team that shares something like KeePass. You can say, hey, come check out the, log into this KeePass vault, and here's the credential. As long as the DLL file is in the same location as the link to the executable, where you open it up with the application, it'll execute. So we're going to go ahead and copy over the keylogger, and we're going to rename it to WinTab32. And then we're going to switch to a different user. This is an unprivileged user right here, but we'll switch to an admin user. And of course, the IT user needs to know a password, so he will browse to the shared file volume. And it could be even, you don't even have to have access to the KeePass, right? If you can have access to the folder where the user has KeePass, you could have this happen. You can see the DLL files hiding in the same location as the link or the KDB file. And when you open it up, everything looks fine. Types in the password. But in this case, it just writes it to the disk. You could have it sent out somewhere else or do something more creative. But there's the password. The cool thing about this is that you can do it remotely. So I didn't call this the red character. I called it the Mallory character because you can send so say you have a network share, right, with KeePass databases. You can drop it there remotely without having any access to any of the crypto. You can essentially bypass the system and get access to that key, which then you would have the ability to open the KeePass and view it. To KeePass's credit, the vulnerability was not something that they introduced. It was in a library that they included. So they did a great job on fixing it right away as soon as we showed it to them. So the other thing that you can do with this, right, is those of you who have seen DLL injection is before might ask, like, why don't we just get a shell? So we'll create a DLL using Metasploit. So we're going to say use Windows payload interpreter reverse TCP. Set a couple of options. Right here, I'm letting the DLL file know where it needs to dial back to. So giving it the attacker's IP address. Create the DLL file with the right name, and Metasploit will write it out. Then we're going to go ahead and set up a handler so that when the DLL essentially dials back, it will be able to send it the rest of the code and get an interpreter shell. So we've got our handler ready to go. We'll go ahead and run it in the context of a job. So Metasploit's now listening for a dial back. We're going to copy the DLL to our target machine just like before. And when the user opens up the KeePass, you can see that it kind of hangs a little bit. You could probably get around that by customizing the DLL, but this is just default. And you can see that it brings back a interpreter payload. So you could send somebody a KeePass database with a DLL file in a zip and say, open this up. And if they had KeePass on Windows before this was patched, you've now got an interpreter shell. So again, enjoy that one. Hopefully you guys can use it and legit pen tests, nowhere else. So last demo, and actually before I start this one, Caleb is back here. Caleb is freaking awesome. This guy, so I found a vulnerability in a tool that he created about 3 weeks ago, and I was like, dude, you're talking right after me at the con, and might be bringing up this tool. Like, I won't disclose this. He's like, no, you should totally talk about it. He's like, I didn't think about this. Like, good catch. Like, you should talk about it. So, like, awesome for him to like allow me to talk about this on such short notice. This is a really tough challenge that he's tried to tackle. But I think the goal of this project called Hypervolt is to make encryption easier for the average user. So see if you can spot the hack as we go. So the user's going to use the tool. He's going to open up a file. And if you're playing Catch the Con, it's a QR code, so get ready. We'll choose a password. And we'll go ahead and lock the vault. And it does a bunch of crypto, like a whole bunch of crypto. And then it gives you the option to save a locked version of the vault. And details of how this works may be coming up next. And then, so once you have the output file, a user can go ahead and open it. And you'll see that it's locked. You have to type a password. So if we're suspicious of it, we can go ahead and view the source. And if we scroll down to the end, you can see a whole bunch of encoded data that's our encrypted file. So this should be, in theory, safe, right? An attacker, it's been encrypted by a whole bunch of different JavaScript libraries, and not just one. You've got multiple levels of encryption. So we should be good. That user can then take that file, send it to somebody else. And once they have the shared key, then the other user can decrypt it. So here's the other user. There's the QR. If you missed it, I'll throw it up again in a second. Okay, so anybody spot the hack there? Anybody have any ideas of where I went wrong except for Caleb? It's a tricky one. So what we're going to do is we don't have access to break the crypto, right? We're looking at the perimeter of the system. We're trying to attack tools. But we do have the ability, if we could man in the middle the communication of that file, or if it was left somewhere unattended, we could add some custom JavaScript to the end of that vault. And then we could set up a server to listen for passwords that come back, and then wait for a user to enter passwords. So this is what the JavaScript looks like. Essentially what we'll do is we're going to create a hook like we've done in a lot of the other examples. We're going to copy the original function, this decrypt file data, and create an old decrypt function. And then we'll create a new one that basically creates an image, appends the image to the page, and as part of that image, it will include the first argument in that that's called on the decrypt file data, which happens to be the password. And then it will send everything as expected back to the original function. So what this looks like from the attacker side is when the user opens up the document that has been tampered with, we'll use netcat to set up a listener on 1, 2, 3, 4. And when the user opens the document, you'll get a HTTP request because the browser is trying to open up an image that is non-existent. And in that image will be, there it goes, the credential, right? So Hypervolt, energetic key, there you go. So if you have the ability to control the tool and the message integrity is not checked by the tool itself, and you can't control the tool checking the integrity, then you can essentially bypass crypto by manipulating the message in some cases. So for anybody that didn't get it, I'll leave that up for a second. Cool. All right. So what to do about it? It's a tricky problem to solve, right? Because we're looking at an attacker that has a lot of privileged access in a lot of cases, or at least in many of these. I think one of the things that we need to do is, as we design crypto solutions, we need to make sure that we're considering the endpoints. So this is something that VeriCrypt did very well. In the Firefox example, I was able to dump memory and get credentials even after a tab was closed. In VeriCrypt, the very next function after it processed the password zeroed out memory. So you can't do that very easily unless you dump memory at the exact right time. So they did a really good job, and there really was nothing you could do to prevent that other than maybe not use Windows, but it's kind of a hard problem to solve. So I think you can raise the bar, though, and make things much, much more difficult. I think some of the earlier examples, like dumping memory, is much, much easier for attackers. The hooking functions becomes a little bit more difficult, and so you can make it harder. The other thing is to continue to focus on protecting the endpoints. If we design crypto systems without thinking about the security of the endpoint, we think, oh, this database is encrypted, so our data is safe. If you're not considering the security of the device that's holding that encrypted data, then your data could be at risk. And finally, focus on both message integrity for both the message and the tool. So this is things like making sure that your tool is being monitored. We don't want backdoor SSH or some of those other tools. So you can use things like file integrity monitoring to make sure that our crypto tools aren't being tampered with. So, questions? No? Oh, good. Yes. Yes, sir. Mm-hmm. Yeah, so I think repeating the question was that I was targeting very specific areas of memory. So in memory, I did a full core dump. The only reason that I grepped for a particular string or a particular ID was so that there wasn't a whole bunch of output. Usually when I do this, I'm just going to do strings and then pipe it into something like less and scroll through it to see what all is available and look for things like password. Occasionally I'll do a search for pass or password or things like that to see what comes up. In this case, I didn't want the screen to be full of a whole bunch of output that didn't make any sense. So yeah, excellent question. But generally, I'll look for whatever else, whatever I can get access to in memory. There are some tools that do that. There's one specifically for network, and I come talk to me afterwards, and I'll look up the name of it. I can't remember off the top of my head, but it specifically looks for things in network traffic, and it will hook certain functions that do that behind the scenes API calls for either API calls or DLL for the browser. So you can get everything before it's HTTPS. And this is what malware does a lot of times, is it will hook processes in the browser so that even though you're connecting to secure bank over HTTPS, it can actually inject code and change it so that it requests something that it wasn't supposed to be or get credentials out of something it's supposed to be over HTTPS. And you see this certificate, everything looks fine because the crypto is good. It's just that you're attacking it between or after the crypto. Sorry, I don't know if that makes sense. Yeah, there's another question. Sorry. Yes, sir. Ah. Yeah. Well, in that case, so I would this would be a good homework exercise, right? Is go and play with it. I didn't test for that, so I don't know. What I found was that in Windows things were a little bit better in memory than on the Linux versions, which was kind of surprising to me. But that was just my kind of thinking around. So the question was whether the password's stored longer because of a 200 response, so that when the user goes back, they can actually resubmit the password when it pops up and says, "Do you want to resubmit this form?" So yeah, I don't know. That's an excellent question. That would be fun to see if if you could somehow secure that by doing a different redirected or doing a 302. But yeah, I don't know if that would help. I suspect that when you look at the browser memory, there's a lot of things that are going on. So it's got to do the request, the get or the post request. So it's got to put that in memory. It's also got to form the DOM for the website to decide how to display it on the page. And so there's a lot of things that are going on behind the scenes to form the DOM. And so memory is just being thrown everywhere. So there's a lot of places that credential can show up. It's not always just in that get or post request. But that said, maybe you could reduce the attack surface a little bit by minimizing the count of it in memory. Huh. Cool. Yeah. Well, report it as a vuln and see if they do anything with it. Cool. Yeah. Makes sense. Any other questions? Yeah. Yeah, I was wondering if somebody was going to ask that question, right? So the question is, if you've got access to the system, why don't you just keylog everything? Why do you target a particular process? It wouldn't make as fun of a demo, for one. for 2, I think you can get a little bit more targeted, minimize your footprint. I think that when you're attacking the entire system, there's going to be a lot of things watching the integrity or processes attaching to things like Explorer, right? Those are going to be much more monitored, whereas there's probably not as much that are going to be watching for individual tools and hooks to those. So you could potentially stay under the radar a little bit better with custom tools. So I don't know of any other great advantages other than potentially just stealth. So yeah, good question. Nobody else? Okay, well thank you. If there's any other questions, I'll be around, so feel free to hit me up and ask me later. Thank you.